Good morning, student. In this class, we are going to derive the expression for total energy of a vibrating string. Suppose we consider a string of length L in the equilibrium position like this. Okay. Now, if we disturb the string with a oscillating force, there will be a transverse wave that will pass through the string, and at any instant of the transverse wave, let us consider the scenario like this. Okay, so now what we are going to consider, we are going to consider a length element PQ of the string, and we'll try to find out what is the value of the kinetic energy as well as the potential energy of the line element PQ as the wave passes through the string. Okay, now since this wave is a transverse wave, therefore vibration of the element PQ will be in a direction perpendicular to the transverse wave, that is in the direction of y. Okay, now let's have an extended view of the portion PQ of the string as shown here. Okay, now the coordinate of the point P is equal to x and the coordinate of the point Q is equal to dx. Therefore, the length of this element along the x direction, it can be given as dx. Okay, now as the line as this element will vibrate in a perpendicular direction at any instant of time, then it's the value of its the value of its displacement and in the y direction is given by this by du, which is shown in the figure. So this portion is equal to du. Okay, now we are going to basically consider what is the displacement of the portion PQ as the wave traveled through the string. That means, suppose initially the portion PQ was like this. Now due to the vibration of the spring, the position of PQ has become like this. So there will be an increment in the length element of the portion PQ. Now we are going to find out what is that length, what is the increase in length due to the oscillation of due to the passing of the wave. Okay, so this increment we are going to basically use for the derivation of potential energy of the string. Okay, now let's find out what is the increment of the length PQ of the string as the wave travels through it. Okay, now as you can see, before the wave travels through the string, the length of the element PQ was dx. Okay, now as the wave passes through the string, there is a displacement in x direction and y direction also. Sorry, there is a displacement in the y direction. Okay, so in this case, if you consider PQ is a small line element, then this we can consider is a right angle triangle, and therefore we can write dl square. Dl is nothing but the length of PQ in this modified position. Then dl square is equal to dx square plus du square. Okay, so we can write dl square, if you take the common dx whole square. Okay, so this is dx whole square, right? It will be 1 plus du plus dx whole square. Okay, so dl square, dl will be equal to dx into 1 plus du by dx whole square to the power half. Okay, now for a very small line element, we can always expand this series, and the value will be equal to dx into 1 plus half into du over dx whole square. Okay, so this is the increased length. This is the length in the position of the string when the wave travels through it. Okay, so this dl is different from this dx. Okay, therefore this difference between dl and dx is now the displacement of the string along the y direction. Okay, so if the new displacement of the string in the y direction, it will be delta L will be equal to dl minus dx. So this value will be equal to this and this will get cancelled out. So this value will be equal to half into du over dx whole square into dx. Okay, now as I have already told you that the displacement is a position of both time and space. Therefore, in place of du by dx, it's always it is always advantageous to use the delta operator like del u by del x. Okay, so partial derivative sign. So what we can write now, delta L is equal to half into del u by del x whole square into dx. Okay, so this is the increment of the length in the y direction of the string as the wave passes through it. Okay, so this displacement we are going to use it in the derivation of the potential energy of the string. Okay, now let's proceed through the kinetic energy of the element dx of the string. Okay, so kinetic energy of the element of the string, say this is dk, because very small kinetic energy, dk is equal to half into m into v square. Let's consider the mass per unit length of the string element is rho. We are considering dx element of the string, therefore its total mass will be rho into dx. Okay, so half rho into dx. In place of v, what we will write, v is nothing but du by dt, because we are considering that displacement in the y direction is u. Therefore, we can write du by dt whole square. Okay. Also, we know that u is equal to nothing but a sine omega t minus kx. Therefore, du by dt will be equal to a omega cos omega t minus kx. Okay, therefore the kinetic energy of the string of the element dx will be equal to half rho dx. Okay, then a square omega square cos square omega t minus kx. Okay, so kinetic energy per unit length, so dk per unit length will be equal to what we have to do, we have to divide dk with dx, because dx is the length element, so we have to divide dk with dx. Okay, so that we will get half rho a square omega square cos square omega t minus kx. Okay, so this is the expression of kinetic energy per unit length of the string. Okay, now what we have to find what is the potential energy. Potential energy of the element pq of the string. Okay, now as you know, the potential energy is nothing but the work done on the system. For example, if there is a force which is responsible for dx displacement of the system, then the work done dw is equal to f dot dx is equal to f dx, provided the force and displacement in the same direction. Okay, here we'll also consider similar kind of expression during the transverse vibration of the string. As I have already told you in the previous part, the force is replaced by the tension T of the string. There will be a tension in the string which is responsible for the potential energy in this case, and we have to multiply the tension with the increment in the y direction, because there is a length increase only in the y direction and not in the x direction. Okay, so what we have to do, we have to multiply the tension of the string with the displacement in the y direction, which we have written as T into delta L in the previous pages. Okay, so potential energy of the string will be now given by T into delta L. Say this is the capital U, right? Just remember the difference. Small u means displacement in the y direction, and capital U is the potential energy of the PQ element of the string, T into delta L. Okay, now delta L, what we have found out, delta L is nothing but, as you can see, half into del u by del x whole square into dx. Therefore, we will write T is equal to T into half into del u by del x whole square into dx. Okay, so half T dx into del u by del x whole square. Okay, then also we know u is equal to a sine omega t minus kx. Therefore, del u by del x will be equal to minus a k cos omega t minus kx. Therefore, del u by del x whole square will be equal to del u by del x whole square will be equal to a square k square cos square omega t minus kx. Okay, so basically what we are going to do, we are going to put this value here. Okay, and this value will be equal to half into t a square k square cos square omega t minus kx into dx. Okay, now we can so the expression for potential energy of the string is du is equal to half into t k square then sine square k square a square and then cos square omega t minus kx. Okay, now we can do a little bit of replacement of this quantity k and t. So it will give half t k is equal to omega square into c square a square cos square omega t minus kx. Okay, so as we have found in the last lecture that the wave velocity in a string c is equal to rho t by rho. Therefore, c square is equal to t by rho. Okay, so we can express this value here, and it will give du is equal to half into t. Then we'll just replace the value of c square. Then it will give us omega square into rho divided by t, because it is 1 by c square cos square omega t minus kx. Okay, into dx. Dx quantity was there. I forgot this quantity. Sorry for that. So tt get cancelled out. This will be equal to half rho omega square cos square omega t minus kx into dx. So if we take potential energy per unit length will be equal to this value. Okay, so half rho omega square cos square omega t into kx. Okay, so now the total energy of the string a square was there, sorry, and there was a square. Okay, so therefore total energy per unit length of the string is equal to kinetic energy plus potential energy. That's the value of kinetic energy was half rho omega square a square cos square omega t minus kx. That was the value of the kinetic energy. And now as you can see, the potential energy is also same. Okay, half rho a square omega square cos square omega t minus kx. Okay, so half will be 1, so rho omega square a square cos square omega t minus kx. This is the total energy per unit length of the string. Okay, per unit length. The one thing you have to remember here, that the value of the potential and kinetic energy will be the maximum and minimum at the same time, because their value is exactly equal and there is no phase difference between the potential and kinetic energy. This is unlike the case of a simple harmonic motion. As one can remember, in simple harmonic motion, when the kinetic energy maximum, then the potential energy was 0, and when the kinetic energy was 0, the potential energy was maximum. But in this case, the kinetic energy and potential energy of the string will be exactly the same, that means it will become maximum and it will become minimum at the same time. Okay, so there is no phase lag between potential energy and kinetic energy. This is one difference between the total energy of simple harmonic motion and that of a transverse vibration in a string. Also, although both are simple harmonic in nature, in one case it was opposite. In one case, the potential and kinetic energy has a phase difference. One become maximum, then other become minimum. But in this case, they both become maximum and minimum at the same instant of time. Okay, now we are interested in the average energy or average total energy, not the absolute value. This is the time dependent value. So if we take the average value, that is the time average. So time average of the total energy per unit length, if we take it as U, then this value will be equal to nothing but 1 by T rho omega square A square 0 to T cos square omega T minus Kx. Okay, so this integration I have done many times, and for a sinusoidal or cosine function, this value is always equal to half. Okay, so what we will get, the average energy per unit length of the string will be equal to half rho square into A square. Okay, so this is the total energy, total average energy per unit length of the string, the per unit length of the string. So it's basically depend upon on the amplitude of the string, because A is nothing but the amplitude of the transverse vibration in the string, and omega is what, the frequency of vibration, and rho is equal to mass per unit length of the string. Okay, so this expression you have to remember. This is a very important expression while we'll consider the reflection or the transmission of the transverse wave for a string. Okay, so in the next class I am going to basically discuss a little bit about those things. Okay, so thank you.